Good afternoon, everyone. So we are starting this current session, which is on OpenFOAM solver for multi-grain solidification. So I am Tanmay, and beside me, Swapnil is there, and Professor Ravik Chaudhury's presentation just happened.
No. He'll just increase the volume, master volume. Speak.
Okay. So what should I? Next slide.
View select. View.
Yeah.
Okay. No, wait there. Yes, sure.
Okay. So this is the grand potential model which Professor Ravik just discussed in his presentations, and for multi-grain simulation we have further modifications here, which includes grain orientation term, this f orientation of theta. This function incorporates the orientation field. The rest of the parameters are similar, and also we have a temperature term here, since we will be also showing some cooling simulation. So we have this grand potential, and grand potential function depends on the temperature as well, beside the chemical potential. And this is the form of the function of orientation field, which I am showing here. The rest of the things are similar to the previous model. So after optimizing the previous equations, the grand potential, then we can get the governing equations of phi and governing equation of mu. And yeah, so here we can see the governing equation of phi contains the theta term, which is the orientation field, and the governing equation of mu, this uh, contains the temperature term. In the field equation also the temperature is present, which comes through this V, which includes the grand potential, since it is also depending on temperature. And yeah, so finally we are showing the equation of this chi, which is present in this governing equation of mu. So just like Professor Ravi showed in his presentations, uh, we can also do multi-grain simulations using OpenFOAM. So here at the left side you can see this is a uh, this contour of phi, the phase parameter, for a binary alloy of aluminum zinc based binary alloy. And at the left side, which I was talking about earlier, the theta term, uh, it is actually different for different grains. So here you can see that theta is acting as a field. So, and it is varying uh, throughout the domain. So this in this simulation, the thermodynamic database of aluminum zinc we have incorporated, and we will see the details of it after some time. And uh,
So I would like to add just one more point. So here this is the theta field, and here hopefully I mean you might be able to see here that we have a scale which says that there are in different grains we have different theta values. So here the addition in this grand potential orientation field based models, each grain is represented by a theta value. So in a grain the theta value will be constant, and then we will have different grains with different theta values. So that's the major difference between any multi-phase field model and orientation field based model. Okay, in orientation field based model we have an extra theta term, and we have only one phi field, which is 1 in the solid, 0 in the liquid, and at the interface region it would be it would have a value somewhere in between. Okay, so instead of solving for n number of phase field parameters in this type of formulation, we just have to solve the phi evolution equation, the theta evolution equation, and then to accommodate the thermodynamics, we have to include the mu equation. So we just solve for 3 equations. That's one advantage over, and that helps in coding in OpenFOAM. So it becomes difficult if we have n number of equations, and if our domain is very large and we have very large number of grains, so we would need to solve for a very large number of phi equations. So that is avoided, and this is a alternate route to do multi-grain simulation.
So this nucleation of the grain, we are also giving a probability for it, which depends on the undercooling temperature. So we will see the details of it in the OpenFOAM case files, which we will run using a smaller domain, and then we can visualize. So like Professor Avik showed before, since this is a temperature dependent simulation, we can also show the cooling, and the temperature evolves according to this curve at the left side, and after the final cool down, we can see the uh, multigrain like we saw in the previous slide. And beside that, in the right side, we have the rate of temperature evolution, where we can see that there is a plateau after the initial drop of temperature, which happens because the solid volume fraction increases, uh, which contributes in the latent heat. So we will see those in detail. And yeah, this is a similar curve which Professor Ravi showed. So here we have compared the uh, aluminium zinc simulation obtained from OpenFOAM with just shell calculation. So here you can see that the shell calculation underestimates uh, the result obtained from the simulation. And now let us look at some of the cases. First, uh, yeah.
So just asking about the
Wait. Yeah. So if you remember that we have shared a MicroSim setup file earlier in during the workshop. Uh, if you just uncompress it, if you uh, extract it, then you will be able to see the OpenFOAM case files, which are also in our repository. So currently we can just show it here. So these are the two OpenFOAM solvers. So I have discussed the binary one, but we will see how to run it, and then I will also show the results for the ternary cases, and yeah, and we'll show what can be, I mean, what can be done from that. Now, to before running all these cases, uh, we have some requirements, so which I am showing in this README file at the right side. So first you need Ubuntu. If you have Ubuntu, then you can go ahead and uh, download the OpenFOAM inbox link from here, and this link we have shared earlier in the workshop. So if you have those, then you can just make a directory. So there was some confusion earlier while installing the, I mean, some of the attendees mentioned, but anyway, so you can just follow these instructions, and yeah, and after you have installed OpenFOAM, just mentioned earlier in Professor Avik's presentation also, he was showing his results also depends on the GSL. Uh, so if you have GSL, then you can go ahead. Otherwise, you will need to install GSL for this as well. And finally, the ParaView comes alongside OpenFOAM in box 20. So you can just invoke it using just ParaView in the command line. And then other than that, for visualization, you will need ggplot, uh, which we can use to check the temperature variation with time, which can be also invoked using this command ggplot. So in case you are new to OpenFOAM, you can find its detailed documentations, which will not be go through in this workshop, but you can, for your own reference, you can just refer to these sites. So finally, let us start looking at the OpenFOAM modules. First, I will change to the directory.
So I would just like to add one more point. So as you can see, to run all of these OpenFOAM codes, you just need OpenFOAM in box, GSL, and GNUplot. That's all. So all the dependencies that we installed earlier, those are for MicroSim. So in that way, this will have less issues in terms of the dependencies. So yeah.
So so first let us look at the binary solver modules. So here you can see three directories. These first two are the case files, which we will show, and this third one is the solver. So before running the case files, you will need to compile the solver. So first let us switch to that directory of the solver. Yeah. So here you can see in the README that we have mentioned. Uh, we are currently at this stage. So where we need to use wclean trust so that it cleans some older binary files of the solver in case you have made some modifications to the solver. Then we can use wmake to compile the solver.
So here this warning is okay. It is just saying that
Yeah.
that variable is not used. That's okay.
So it takes some time for compiling. Okay, so compilation is done. We can actually check it by uh, from this environment variable. So these are the standard environment variable of OpenFOAM. So this you can see binary is written at just recently. So this is the name of the binary. Now let us have a look at the case directory. So first we will look at the case directory binary grain growth. So this actually is independent of the temperature evolution. So here we are keeping a constant undercooling, which we will come later. First, let us look at the different directories. So we have zero directory, which basically contains all the initial values and uh, the initial conditions of the parameters, and then we have a constant directory, uh, which contains the material properties and temperature and all these TDB thermodynamic database, which Professor Avik has already discussed in his presentation. And then we have this system directory, where we have block mesh. So block mesh contains uh, the size of the domain and the discretization, and control dict contains all the time step and name of the solvers or write time, all those things. And decompose contains how many processors you want to use, and FB schemes and FB solution contains what kind of solvers you want. So we will come to all this in detail. First, let us look at
So by the way, these other
Yeah.
folders that you can see, dynamic. Just go back.
yeah.
So these other folders, dynamic code processor 01. So those will be created once you start the simulation. So
Yeah.
previously a simulation was run in this folder, so that's why those files are appearing.
Okay. So to clear this, we can use /all clean. So it will clean all these older files. Okay. Another thing is we need to make it executable. All clean and all run must be set as executables. So let us do it first. Yeah, I need to change the date. Okay, now we can execute all clean. See, now we can see that we have all those older runs cleared, right? Okay, so let us have a look in the zero directory first. What are the initial conditions? So, for example, let's see at fee.org, right? Yeah. So here we will be using uh, initial value of so here we will be using initial value of 0 and it is uniform, and then we have cyclic boundary condition, which is basically repeating throughout the domain.
So it is same as the periodic boundary condition.
Yeah. Then if we look at this file mu original, yeah, so here we can see the uniform we are taking from this variable. So why we are taking this? Because we need a driving force in this simulation, which we are getting from the undercooling. So let us go back and check what is the yeah. So we are now at the constant directory, and we are looking at the transport properties. So in transport properties, we can see all the properties which were present at the governing equations. So here we have gamma, epsilon, and all these parameters. You can see these correspond to what Professor Avik has used in his simulations. So you will find them in the example in files. Now we were talking about the undercooling temperature and the equilibrium temperature. So for that we have this temperature where we are specifying the undercooling temperature at 857 Kelvin and the equilibrium temperature at 870 Kelvin. So it is at 13 Kelvin undercooling for aluminium zinc. Now since we are reading the temperature from that file, so we can obtain the values here, and then uh, we have two switches here you can see SW pool which is 0 because we are just keeping a constant undercooling. It is independent of, currently this simulation is independent of temperature. And then we have a switch equals to 1. It is for enable orientation field. So because we are looking at the effect of the orientation field, so we will keep it as 1. And then we have the scaling factor at the theta equation, which I showed earlier, and this is the initial seed radius from where it grows, and the number of seeds we will be using 4. Since this is a small domain, uh, and we have very limited amount of time, so uh, number of seeds 4 will be sufficient for it. So this rest of the files which Professor Avik discussed, so those are similar in nature. It's like this Hessian of liquid and this composition files. So these are all temperature dependent, but we are taking at a constant temperature for this current simulation. So we will be using GSL for that requirement. Now we are looking at the block mesh. As I have said earlier, that we will be running a smaller simulation. So we have uh, 200 cells at the x direction and 200 cells at the y direction. So it has total 40,000 cells, and this is a 2D simulation. So at z direction there is only one cell, and you can see the boundary conditions here. We are using periodic boundary condition or cyclic boundary condition throughout. So these are the standard OpenFOAM case files which you can find from the user guide. Now we are looking at the control dict. So here we are we are specifying the name of the solver, which if you remember that we checked earlier after compiling the solver. Yeah, it is still there. Okay, so we are starting the simulation from the beginning. So we are specifying start time and start time at 0, and then end time we are specifying a small amount of time, since it is a small simulation, and this is the time step delta t. Yeah, and this is the write interval. So we will be writing the results at this interval, and yeah, we have write format, write precision, and yeah, these things you can look up from the OpenFOAM user guide. So this is the number of processors. We are using simple method for decomposing, and yeah, so 2 processors will be using. So here we are specifying what kind of schemes we need to solve the differential equations. So in OpenFOAM we are using finite volume method, and that is implicit. And further we have every solution. Uh, Here we can specify the tolerance for all these equations. So we have 3 equations for the binary case, mu, phi, and theta. So before running the simulation, I think we can have a look at the all run, what it contains. So this all run script runs all the utilities step by step. So initially we will be running the block mesh, and then we can just get the uh, initial conditions from these files, fee.orig and for all these three variables, and then to get the driving force, we need to specify one initial mu, which we can get by running this uh, mu initial script. So there is a script outside, you can see. So that basically calculates the initial mu from the at the undercooled temperature by using GSL from the thermodynamic database. So finally, we can use the decompose. We can just decompose the domain and then run the simulation. Now let us uh, start running a sample simulation. So I'll keep the readme open so maybe. So we just saw that initially it runs block mesh and then it calculates the initial value of mu and then decomposes the domain and then finally runs the solver. Now we can check the progress. Okay, one time step is written already. Also we can look at it in more detail. Let's see. Okay, two time steps got written. So as we can see in the readme file at the right side, we can also check the results at ParaView. But yeah, one thing we must notice that currently these are, I mean, the results are still decomposed. So we have an option to reconstruct the domain before running ParaView. So yeah, we can do that here by using reconstruct par, and yeah, if we do reconstruct part, then whatever time steps are available, it will just reconstruct for all those times. The result we can see for all those time steps. Okay, so now let us launch ParaView. The simulation is still running at in the background, but we can visualize the result using ParaView. Yeah, here we must notice that case type. Currently, we have already reconstructed the case, so we can use reconstructed case. If you have not reconstructed it, you can also use decomposed, but we will go ahead with reconstructed. Yeah, so here we can see that the grains are nucleating, and also as I have mentioned in the slide, so there is a probability which we have incorporated in the solver, uh, which depends on the undercooling, so which will determine whether a grain will nucleate or not. So this is the phi, and we can have a look at theta. Yeah, you can see there are 4 grains, but theta values are different for all 4 grains. So this shows that this is the effect of the orientation field. You can also have a look at mu.
So this simulation is still running, and we constructed only for a couple of time steps. So, we can
switch to decompose.
So we can just go to decomposed, and then if you click right. So here you can see that the number has increased from 3 to 11 now. Max is 11. So, and then if we keep refreshing, that number will update. So as the time files are generated in the processor folder, decomposed folders, so by refreshing it, we can just visualize it, and then we can play here.
Okay, so as you can see, there is a dendritic growth at the top left grain, so it will grow further. So yeah, anyway, if you take a larger domain, then you will be able to see that there you can accommodate much more number of seeds, which I am going to show now. Yeah, actually we can disclose the paraview. Maybe you can just stop this simulation, and due to time constraint, because we also need to show the temperature variance. So in the cooling simulation, we can also show the effect of temperature and grain growth, which is much more interesting. Okay, so as you can see, we have another case here for the binary solver, which is binary cooling. So this also we can just clean up. As you can see, all these previous results got disappeared. So let us look at what is the difference here with the previous case. So in the transport properties, as you can see, uh, we have turned on this switch equals to 1, just to show the temperature dependence. So here the governing equations will get affected by temperature, and the temperature will evolve by following a heat dissipation law, uh, which is there in the solver. And I think that's all good. So the rest of the things we are keeping same, the number of seeds and seed radius.
In the previous simulation as well as this simulation, we were nucleating the seeds randomly in the domain. So every time we would run the same simulation, it would nucleate the seeds at different locations.
Another thing, yeah, I want to mention, that is we have a heat dissipation term here, that is Q dot, which Professor Avik was mentioning during his presentation. So uh, by changing this Q dot, we can change the rate of temperature evolution. So if we keep larger Q dot, then we will see faster cool down. Else for smaller Q dot, we will have slower cool down. So yeah, as he said, slower cool down is equivalent of casting processes, and larger cooling rate is equivalent of additive manufacturing. Yeah, maybe we can remove this as well. Now let us run this simulation using the same process. So just like the previous simulation, it will just follow all the same modules, and yeah, it is running. we can also check the progress. Yeah, one time step got written, and then check further. Yeah, it is still running. Actually, we can directly look at the paraview, since we can also check the decomposed results, so without reconstructing it. So, yeah. So as you can see, even if we have given total number of nucleations as 4, since there is a probability, so only 3 of them has nucleated. So there is a slight difference you can notice at the orientation field between the grains. You can also have a look at the temperature evolution using GNU plot. Yeah. So at the x-axis you have time, and at the y-axis you have temperature. So the temperature is decreasing, and you can see a slight saturation, and again it decreased. So we will show the result for a larger domain where you can see how it goes further. Temperature is saturating. Then it increases.
Anyways, you can show the
Yeah. Anyway, so we can just stop the simulation because of time constraint. So I'll be able to show more simulation on ternary grains as well. But before that, I want to show the results of this case when we run it for a larger domain. Yes, this is the result which Professor Avik has already shown during his presentation. So it continues growing in this way. This is a 1000 cells by 1000 cells domain, so it has total 1 million cells in it. So you can see the grain finally grows to this when the temperature we can see as I have shown in this slide. And yeah, the corresponding orientation field also we can look at that.
The different grains are growing in different directions.
So so as you can see, we have another solver module which deals with the ternary alloys. So here we have investigated nickel, aluminum, molybdenum, which Professor Avik was also discussing. So here, yeah, and again, like the similar binary module, uh, here is the solver for the ternary case. So similarly, we will have to compile it again while running. And yeah, before that, maybe I can show that for the ternary case of nickel. Yeah, nickel, aluminum, molybdenum also, this shows a similar grain growth. And here is the temperature evolution and the rate of change in rate of temperature. Now let us have a look at the solver. So again we will need to do wclean and wmap just like the previous binary solver. Since this is a ternary solver, we have an additional so we have equations for we have two equations for the composition evolution, so which gets reduced to evolution of chemical potential. So because of that it runs a bit slower, since we will have four equations this time. Now we can have a look whether the solver, whether the binary is created. Yes, it got created. So let's switch the directory and let us directly move to the ternary cooling, since we have already shown the temperature independent case. So here again we will need to execute all clean. So this directory is clean now. So yeah, how much time is remaining?
What 40 minutes? No 40 minutes. So you can show them what changes have happened in the all those files.
Right, correct. Okay, since just like I mentioned that we will have two parameters for the chemical potential corresponding to two compositions, and so here those are. But just like the binary case, here again we are taking initial mu, which acts as the driving force. By the way, here the temperature, the undercooling we are just keeping 1 Kelvin. Yeah, in the previous binary cooling case also we were using 1 Kelvin undercooling. So since it is since the temperature is reducing with time, that that gives the effect of cooling on the multigrain simulation. Now let us look at the composition. Yeah, so we have temperature and uh, two components here, aluminium and molybdenum, both for solidus and liquidus, and similar things we also have for the Hessians. Yeah, aluminium and molybdenum again. So this I think Professor Avik has already showed in his presentation. So I will just move on. Yeah, we can also have a look at the thermal. So like the binary case, yeah, I forgot to mention during the binary cooling simulation, we were also using a um, temperature dependent heat capacity and latent heat. So yeah, here again we are using GSL to calculate them at the current temperature. Now let us look at the transport properties. Yeah, it is more or less same with the binary one. The difference is we have the diffusivity matrix here, which Professor Avik discussed. So for ternary case, we have this diffusivity matrix. The first one, the D underscore A, this corresponds to the solidus or the alpha phase. So we are keeping it as 0 since there cannot be any diffusivity within the solid, and then for the liquid the diagonal terms are non-zero and the off diagonal terms are 0. I think rest of the things are similar to the binary case which I just showed. Now let us just run this simulation. You can again track the progress. Okay, it will run a bit slower since we have 4 equations, and but we can check the details further. Yeah, so here we can see that the chemical potential equations will require simultaneous convergence until the initial norms are reduced below a certain value. It will keep iterating. can check out the temperature if it is there. Okay, nothing is written yet. Okay, we can have a look at the first time step. It just got written. Okay, so 4 out of 4 seeds got nucleated here, but we have only one time step till now. Yeah, all four of them got a different orientation, and these are the mu for two different components. But we can hit refresh and check. Not.
Maybe you can change the right time.
Yeah, we can do
Right
it.
hand.
That will just write difficult. So just wait, there is time. Meanwhile, we can check at the temperature. Yeah, it's there. So it started from 1654 Kelvin. Initial 1 Kelvin under cooling, and then temperature kept reducing, and then again increased due to solidification, and then again hit a plateau. So recoalescence is happening here. Okay, we have another time step. Yeah, the temperature got saturated and then again started reducing.
You have sincere through Session Workshop.
So yeah, so during my presentation I showed this ternary simulations, which has the domain size of 1 million cells, which is much larger than the simulation we are running currently. So we can have a look at the movie of this results. So this is for nickel, aluminum, molybdenum. We can see dendritic growths already. So basically till this stage it reaches over 80% volume fraction, as I have checked before. 80% volume fraction of the solid. Now let us have a look at the orientation field. Alright, yeah, that's fine, thanks. You want to mention something in comments? So both of these binary and ternary simulations, as I have shown here, it ran till the stage where the temperature and the lowest temperature which is available for solidification. Is 790 Kelvin, around 790 Kelvin in this case, and in case of aluminium zinc, and in case of nickel aluminium molybdenum, it is um, around 1560 Kelvin. Yeah, maybe we can, yeah, let's see how it has gone. You can stop it. I think, yeah. So, yeah, anything else is there?
So this was the complete overview of both of the solids that we have. I mean, for binary as well as ternary, and then in isothermal condition, and then in the continuous cooling cases. So, so all these things that we explained today, and the thermodynamic or the alloys that we talked about, the aluminum, zinc, and the
Nickel aluminium.
yeah, nickel, aluminum, molybdenum. So for both of these, so these are all available on our GitHub repository. Can you open and show them?
So yeah, I have also shared them in multiphysics modules, so you can have a look at the constant directory of the any of the case files. just like I was using them during running. Yeah. So these are the thermodynamic files for the compositions and the Hessian of the solidus phase and the liquidus.
And as Professor Abik mentioned in the previous sessions also, that you need to have the thermodynamic database file, that is the CSV files, in the increasing order of the temperature. So that is true for this case as well, because we are also using the GSL libraries. And just go back to the folder.
So, okay.
So yeah, I mean, so this OpenFOAM does not have a GUI interface like we had for the MicroSim, but here it's pretty intuitive. So you have to just make changes in the 0 time folder, and so for all the initial cases, our initial files are, I mean, you might not have to make any changes here, and then depending on what thermodynamic database or what alloy system you have, accordingly you will have to make some changes in this mu initial.cpv file. Okay. So here you have to mention the correct paths. Right?
These are
file
commented.
names.
Yeah. So yeah, as you can see, we are going to calculate the initial mu from the script, from the C++ script, and yeah, you can see that we are using the liquid Hessian, which is in the constant directory, and the composition CSV, which is also in the constant directory. And also, since this is a cooling simulation, we are also
Yes, so no change needs to be made.
yeah,
With the Alloy system, everything is there at the
Yeah, I mean, if they have a different file name, it has to be accommodated here.
no, it will never have a different file name.
oh, okay, right.
We
File
don't
names
have
are
the same thing.
Yeah, yeah, that is
Okay.
consistent.
Oh no, they are always.
Hmm.
The same name change. So this is something that one can take in from the same the phase name. You can
Yeah.
take it in the constant file,
Right, right.
and this can then let
Yeah.
be left unchecked.
For example, yeah, we
But
are
at least
using-
they should know that this is where they have to do things.
No, if you don't make them change, then it will be better.
Fine.
Handle
Yeah.
it at the constant file level.
Yeah.
So
Take the same.
instead of changing things in this .cpv file, you just use the same file names in your constant folder where you have the .csv files. So use the similar names so that you don't disturb the script.
No. I'm saying
Suppose we
take
have
the
HCP instead of
take the
FCC.
file names, take the phase names in the
Yeah,
constant folder, constant file,
Right.
and make this read the constant file such that the file name, correct file name gets created here. So you
Right.
don't have to touch this.
Right, right.
No, that didn't go into the
Right.
Here,
So yeah, in this, since we are using this is not a multi-phase code. This is here we only have the FCC phase and the liquid phase. Suppose we have HCP phase as well. So in that case, to manage consistency, to maintain consistency, we can also have the other, I mean, the CSV files corresponding to the other phases. We can also access from the constant directory. Right.
The addition is that composition underscore CPA1.
Yeah.
That name can be created here after
Yeah.
reading the phase name in the constant
Right,
file.
right.
So the input can be made in the constant file.
Right, right. So anything else you want to mention?
Anyway, that can be adjusted in the repository.
Yeah.
close this. That's it.
There is just, I mean, development, I think, right? We don't have another thing.
Anything else they have to change? That's all. That's all. Then we already covered this.
Yeah, so we can open the session for questions if anyone have any questions.
there any questions? So earlier someone had some installation issue also in this.
So in case of difficulty in installing, we have this readme file in the repository as well, so you can just follow this from the beginning. It is very straightforward, so and it works. It worked for all the systems here.
So any questions from the audience?
Okay.
Same code,
Yeah.
you can have several pooling. So let's say one tool is solidification module.
Right. Can we use the mic of the audience?
Yeah. Priyanshu.
Mic.
But still that audio will not
Audio
go here.
will go there?
No, it will not go
It
here.
will not go here. Okay.
It's fine. Okay.
Mhm.
So what I was saying was that this same thing can be extended or will be extended.
Right.
You have the solidification tool, but you can also have multi-step agent.
Right.
Which can be just incorporated to this. So there the input would be multi-step temperatures.
Right.
And those can be input and you can suggest holding times
Right.
and the temperatures as inputs, which the same.
Right. So
That can be something that can be added.
Yeah.
One of the modules for both again binary ternary, but precipitation.
Right. Yeah, so these solvers can be modified further for multi-step aging, where we can evolve the temperature stepwise. We can specify the temperature in that way.
So we will have the cooling for some time, and then we can hold the temperature, and then again after some time again we can cool it further. So we can have multi-step aging processes, which can be extended with this model.
Yeah, so precipitate growth can be done like that.
So that can be one future release feature.
Yeah.
So this would be one of the future release features as well.
So if there is no further questions, then what shall we do?
Yeah, so if there are no further questions, then we can end the session here. So this was today's last session. Tomorrow we'll start again at 10 o'clock.
What is the schedule? Just go through the schedule.
Yeah,
Yeah.
we'll share the schedule.
Yeah.
So there will be a small change in the schedule in the yesterday. Tomorrow second session is hands-on experience for getting calculations, and that will be changed to title, a different title. That will be a talk right of the assignment. Okay, it will be on first principle estimation on interpretation of this element. But you can just say that session is changed to a separate talk on estimation of interpretation.
So this is tomorrow's schedule. So the session will start at 10 o'clock. 10 to 11:30 we have the first session on OpenCL. Then second session will be on CUDA based solvers till 1:15. Then we'll break out for lunch. And next, this hands-on experience for getting calculations. So this is replaced by another session by Professor Vaishali. She'll be talking about the interfacial calculations in this session. And then in the second last session we'll have the post process. So we will again go through. So you have already seen the GUI. And you have seen some part of the post processing, but we'll cover it in proper sequential manner and in detail in tomorrow's session in this post processing. And then in the last session we will compare micros and microsim.